This video is an example of a modeling liquid-liquid equilibrium problem. We're going to try to replicate this curve. This comes from the Dom and Visco textbook, figure 13.1. It shows the methanol cyclohexane liquid-liquid equilibrium at 100 kilopascals. So our problem statement formally says we have the experimental data as shown below, so it's not tabulated, it's graphed, which will make the problem a little bit harder, but we can still do it. Using the one parameter Margules model to model this liquid-liquid equilibrium, calculate the parameter of that Margules equation for 300 Kelvin. Then we're going to use that in order to try to replicate the entire curve, and we're also going to need some information about the excess molar enthalpy, and that'll come into play a little bit later. So the first thing I'll need to do is go into my notebook and grab some relevant equations. I'm going to need the equation for phase equilibrium, and then I'm also going to need the one parameter Margules model. Here are those equations. The first one is the phase equilibrium relationship for component 1, which we will assign to be methanol. Second equation is the equilibrium relationship for cyclohexane, and the gammas are given by the one parameter Margules model. So looking at these equations, looks like I have a few unknowns, but if I recognize that I have experimental data, I have way less unknowns. So at 300 K, which is what we want to find the A parameter for, we can look up on the diagram. So for 300 Kelvin, what is the mole fraction of my components? So my mole fraction of methanol is given on the x-axis in this diagram, and I said methanol is going to be my component 1. So I can arbitrarily assign which one is phase alpha and which one is phase beta, by the way, too. So mole fraction of methanol in the alpha phase, we'll say, is on the left-hand side. We'll say that is 0.13 or so. So X1 alpha, which is again methanol on the left side, is 0.13, which means that my X2 alpha is simply 1 minus this. So this is the mole fraction of cyclohexane, and in general, the mole fractions for the individual phases must sum to 1. I can also look up and find X1 beta on the same diagram at 300 Kelvin, let's say 0.82. And therefore, X2 beta is 1 minus X1 beta. All right, so now that we have those four terms solved for, looking at the equations for the gammas, I recognize that X1 and X2 are solved for already. It's just the alpha parameter that we need now. So I'm going to plug in the one parameter Margules expression into the phase equilibrium equations and see what I get. This is the result when I plug those equations in. So I'm plugging in the gammas for the gammas in the phase equilibrium relationships. So now I've got two equations that I can use to solve for the one unknown. So everything in this equation is actually known except for the A, and that's the same thing in both equations. So I could probably solve this algebraically. I could do some simplification here and I could obtain the answer for A, but that looks to be a little work, and I've got Excel open already, so I might as well just use my favorite goal seek. So I'm going to need an initial guess for A, and then with my equation 1, so phase relationship 1, I'm just going to goal seek it to 0. So I'm going to use the formula equals X1A times exponent of A times X2 alpha square minus X1B times exponent of A times X2 beta square. All right, not 0, obviously, because I haven't guessed properly. So I'm going to data, what if analysis, goal seek, set value of this cell equal to 0 by changing my cell of A. And I'll run goal seek and find A is equal to 2.54. Now notice I only used the one equation. I didn't use this other equation. So why didn't I use this other equation? Because I didn't need to. Remember, if I have one unknown, I only need one equation to solve that one unknown. But since we have this other equation, let's pretend instead of using the first equation, we use the second equation instead. So instead of phase relationship 1, what do we get if we try phase relationship 2? Would we get the same answer? I would hope that we'd get the same answer, or at least somewhat close to it. Otherwise, if we have a big contradiction here, how would we know which equation to use? So let's go ahead and try it. So this is equals x2 alpha times exponent of a times x1 alpha square minus x2 beta times exponent of a times x1 beta square. And I want to do it separately actually just to see what answer I get. So I know it should be close to 2.54, right? And I want to switch all my cell references for the parameter a. I want to change them to reference this cell instead. So goal seek again. What if analysis goal seek and set cell B14 equal to 0 by changing cell in the A. And I don't get the same exact answer. I get 2.4. So it's not all that different. Like I said, it's similar, but not exactly the same. So a logical question here is, which one should I use? Should I use one or the other? Maybe I take the average and I report 2.47. That's not necessarily the best answer either. And in this case, we're going to do something similar to what we've done, which is where we try to minimize the error. So in other words, use the one parameter that fits both equations best. So the way I'm going to incorporate both equations is that since I've solved each of them for 0, if I add them together, they should still equal 0. But I don't want to just add them like so, because if I have one minus the other one, then if I have positive or negatives, they're going to cancel out. So I'm going to do the same thing where I square it such that if there's a negative, it'll just get squared. So I'm going to make another function here. So this is going to be my best fit A. And I'll have my initial guess as the average between them, just visually calculating it. So my function to minimize, it's not really a sum of squared errors, but I'm going to do both equations squared and then added together. So it's going to be equals, wait a minute, I don't want to take that. I want to take the function, so copy, and then when I paste, I want to paste the formula, but I want the formula to reference my best fit A. All right, and I want to take this one as well. So copy formula. And this formula's got a reference A. Whoops. Undo it. Anytime I'm referencing A, I want to reference the best fit A, and I want to keep all my x1s, x2s, so on and so forth constant. And the other thing I want to do is square them. So square it, and that'll get rid of a negative. Square it, and it gets rid of a negative. And now I want to add these together. So equal, well, I don't have to click sum if there's only two. I'll just add them both together. So this is phase 1. It's not phase 1, it's relationship 1, component 1. Component 2, and this is the sum. And what I really want to minimize is this sum column. So what if analysis, goal seek, set it to value 0 by changing cell in the best fit. And let's see what happens. Oh, it's not converging. Maybe I'll try solver to minimize. So I want to minimize the cell, set it to a minimum by changing variable cell E10. Let's try that. Okay, that worked. Solver found Solver found that the best fit A was pretty close to the average in between them. So, and the average wouldn't have been necessarily a bad guess here, but it's always better to use this minimizing strategy other than just taking just a linear average. So my best fit A in this case, I would call this value of 2.47. So that's the first part. Now we're going to use this best fit A parameter, which is a function of temperature, in order to find or try to model this entire curve. So in this, we're going to need to assume that the excess molar enthalpy of the mixture is this function as described in the problem statement. So this A parameter is going to be a function of temperature, which is why we need this. So the first thing that we'll have to do is to figure out the functionality of A with respect to T. And for that, we're going to have to go back to class 18, and I'm going to grab some more equations from my notebook. So class 18 was talking about how excess Gibbs free energy changes with respect to changes in temperature. And we haven't talked a whole lot about changes in temperature just because in vapor-liquid equilibrium, we focused on pressure just because temperature was so much harder to calculate because there's some extra terms there. But for liquid-liquid equilibrium, mostly these graphs are going to be in terms of temperature because these curves are not really a function of pressure as much. Whereas in vapor-liquid equilibrium, pressure and temperature both equally contribute. But this is the equation that we had, and this is why we need an expression for the excess molar enthalpy. So we know how the excess Gibbs energy divided by RT is changing as a function of temperature. So I'm just going to plug everything in. This, by the way, this GE over RT is equal to A x1, x2. This is the one parameter Margules model. We also have our expression for excess enthalpy there that we can plug in. So I'm going to perform that algebra. So on the left-hand side, I've plugged A x1, x2 into GE over RT. And then because the number of moles are constant, so N1 and N2 are being held constant, therefore X1 and X2 are also being held constant. So that can come outside of the derivative. On the right-hand side, I've just plugged in a 5,719 X1, X2 in for excess molar enthalpy to obtain this side. The next step is I can simplify and integrate this expression after I separate the variables. So X1, X2 are on both sides, so those cancel out. I could take the dt over to the other side, integrate both sides, and I'm integrating from 300K to whatever temperature that we have. So this step is all trying to figure out what the functionality of A is, such that I can express A as any temperature other than just the one that we calculated. So we only have a value of A for 300K. We don't have a value of A for the rest of the temperature. So that's what this step is trying to do. This is just going to be a formula that I use eventually to plug in for this model. So now in order to plot the curve, I'm going to choose several values of temperature. So I'm going to set the temperature. And when I set the temperature, I can calculate what the value of A is. And then once I calculate what A is, I've got two equations for two unknowns, which are going to be X1 alpha and X1 beta. Right, X2 alpha is not an unknown because I have a constraint that relates it. So I have 1 minus X1 alpha is X2 alpha. So down here, I'm going to plot a range of temperatures. And by looking at the plot, I know that my data should go from about 290 to 320. So I'm going to start a little bit less than that. I'm going to see what happens. So I'm going to say 280 and then increase by 5 every time and plot it that way up until 320. Actually, I'm going to keep going and see what happens. All right, so this column is going to be my A of t. And for A of t, I'm going to simply plug in what my expression is. So A of t is equal to, bringing this over to the other side, A of 300K is something that we know, right? So we calculated this in the first part of the problem. So it's equal to A at 300K minus 5719 divided by 8.314. And these units are consistent, right? So it's joules per mole, R is in joules per mole Kelvin, and then we've got a 1 over Kelvin here. So times parentheses 1 over 300 minus 1 divided by whatever t. All right, so we've got A is missed a parenthesis. How do I know that I missed a parenthesis here? Because I know that A of t should be 2.47. Actually, I didn't miss a parenthesis. I missed a dollar sign. So E10 has to be dollar signed. All right, copy that all the way down. And at 300 Kelvin, I've got 2.47. Yep, perfect. Okay, so this is my A parameter as a function of t. Now I've got to solve for my two unknowns, x1 alpha, x1 beta. All right, so once again, these are my two equations, and I'm going to employ the solver technique to solve this system of two equations and two unknowns. Now, you may be able to algebraically manipulate these a little bit in order to make it a little bit more direct to solve, but once again, I already have Excel open, so I'm just going to go ahead and use Excel in order to solve it. So I'm going to make columns for x1 alpha and x1 beta. This is going to be my initial guess, so I'm going to just plug in 0.5 for both. Once again, just an initial guess, and then I'm also going to simplify things, so I'm not typing in 1 minus x1 alpha all the time. I'm going to make an x2 alpha and an x2 beta, and in this column I'm going to say it's equals 1 minus x1 alpha, and this column is equals 1 minus, not 11 minus, 1 minus x1 beta. Copy down, copy down. So I've got two equations here, the first equation and the second equation. Both have to be set to 0, so I'm going to do that by bringing the other side, one side over to the other, as I usually do. So x1 alpha times exponent of A times x2 alpha square. And I don't have to dollar sign anything, so there is no set value of A because it's going to change as temperature changes. So I'm going to use that value of A for each individual temperature. Minus x1b times exponent of A times x2b square. Okay, that one's equal to 0. Interesting, why does that one equal 0? I wouldn't have expected that. All right, let's keep going. Second equation, x2 alpha times exponent of A times x1 alpha squared minus x2 beta times exponent A times x1 beta square. Interesting. Why do I keep getting zeros? Let me see if I pick a different. Oh, because that's, again, that's the trivial solution, remember. So I know that I'm going to have need an initial guess that's close to what my actual answer is going to be. So I'm going to choose, let's see, at 280, I don't have data for it. I'm just going to say it's equal to 0.1 and 0.9. And let's drag those all the way down. So again, whenever my compositions of the two phases are equal, that's a trivial solution because that has to be true. If I only have one phase, then my composition of the two phases are going to be equal. So let's now solver and set my objective going to be equal. My equation 1 has to be equal to a value of 0 by changing variable cells. Now I'm going to try and do these all at once. I'm going to see how it works. So hold control again to select multiple cells, and then subject to the constraints that all these are also equal to 0. And I want to add a constraint that all my equation 2's are equal to 0. And uncheck the box and hit solve. Give it some time. And okay, let's go through and plot now. So I want to plot, it should be one curve, but because I have two unknowns, I'm just going to plot them on the same curve and try and see if they connect. So I want to insert a graph. Oh, that looks weird. Let's select data and series X values. Oh, this is supposed to be my series X values. My series Y values are my temperatures. Right, and I want to add a series of Y values and X values, X1Bs. Oh, wow, okay. Something is weird here. All right, I've rescaled this plot. So temperatures on the y-axis, composition is on the x-axis. I've got this weird, weird point right there. And I don't know what's going on, but this one didn't look like it works for whatever reason. So maybe I just have to try it again. But you notice if I'm looking at what my x1 alphas are, they're all increasing until I get to 0.337, and then it goes back down to 0.24. Got the same thing happening at x1b. So this solution that it gave me was the same solution. So usually when it gives you the same solution, that's not a physical answer. So if I just delete this data point, you notice it starts to look kind of more like it should. But I don't have all the temperatures that I need. So I'm going to need to plot some more temperatures here. So I'm going to keep going. So I'm going to go up to, let's try 370 or so. And all these are going to be copied down. And I want to increase my plot range. Of course, I'm going to have to solver these again. Oops. Undo, drag down, drag down. All right, obviously that's not how it's supposed to look. So I'm going to try solver again, data solver, and let's see, I just want to increase. I'm going to try solving them all at the same time again. Subject to the constraints, let's see, change my reference to be all of them. So this is kind of annoying having to reprogram solver like this. But hopefully it works this time. Okay, solve. And I'll pause while it goes. Okay, it tried to solve this one again. That was a weird point. If we remove that point, it's looking like it's converging, but not quite. I'm going to try and copy these initial guesses down and see if that fixes it at all. But I need a couple more data points. So copy these all the way down and try it one more time. Changing variable cells, all of these, and constraining those to be equal to 0 and changing all of these equal to be 0.